Hello, welcome back to, well, this is not SAS from scratch. This is part of the SAS Advanced series of topics on my channel. I'm Jan. If you followed along with SAS from scratch, you probably know me from all of the base videos that I've done. And I have been sort of putting off doing the advanced videos just because, one, there's a lot of effort to sort of, prep for all of these. But there is one specific thing that I've wanted to cover because it shouldn't take too long. That being said, I do tend to talk a lot. And two, I don't see a lot of it. You don't see it talked about too much on YouTube and even in the industry. It's just not something that people cover too much, and that is PROC FCMP. It'll be in the title of the video, so it probably won't be a surprise because you clicked on it. The whole point of PROC FCMP is to allow you in SAS to write your own functions. So FCMP stands for Function Compiler. F for function, CMP is an abbreviation for compiler. And it actually allows you to do two things. The first is to write functions and obviously call them again so you can use them. The second one is subroutines, and we'll see how subroutines and functions differ from one another as well. So first of all, how do we start just defining a function? So let's say we want to create a function, and I'm going to use basically pseudocode for this. So let's say we want to do function my square, and we are going to take the value x in there. And what we want to do is we want the function to start. We want to return a value x times x because that is what square means. You times a number by itself. And then we want to return that value back to the user, to the wherever that call came from. It goes back there with the result. Now, in a lot of your other languages, for example, if you wanted to look at C, you would do something like the following. C, Java, I'm just sort of giving you a general idea how it would be done. You would define a type. Now, of course, SAS doesn't use types except for character and numeric, so we're not going to worry too much about that. But you would do something like int my square accepts an int of type x, open the function with the opening brace, close it with the closing brace, and you'd say something like return x to x times itself, and semicolon. If you were programming in R, you could do something like my square is a function which accepts x, and you would return x times x. So that's fairly straightforward. Most of the languages do something very similar to this, and for all intents and purposes, so does SAS, except with SAS you need to wrap it in PROC FCMP. And likewise, when you call that function again as well, it needs to be wrapped in PROC FCMP. And the syntax for PROC FCMP looks something like this. Actually, it looks exactly like this. You need to specify an outlib. This outlib is where your library of functions is going to live. So you need to give it a library. You're going to sort of connect it almost to a data set. And then within that data set, you're going to have your package of functions living there. And within that package of functions, you can specify several functions and even subroutines that you can refer to later on again. Now in this case, we're going to use the work library. I'm going to just call the dataset level funcs, and I'm going to call the package Jan's math, because these are all my math functions basically. So I'm going to do a few just to give you a feel of it. We're going to do stuff like a square function, a power function, and then also one extra special one, which I always enjoy, but I'll leave that as a surprise for later. So, PROC FCMP is one of those procs that we need to close, I believe, with a quit statement. I should probably go and double check the syntax for this, but I believe it's the quit statement. And then give me 1 second, please. I just want to double check that I'm not, yes, I am correct. It is definitely the quit statement. So like proc SQL, you end proc FCMP with quit. You quit the subroutine completely. And notice here that this library we're pointing to here is of the form libref dataset and package. So this is what we've got here basically. Let's talk about writing our first function, that square function that we've talked about. I'm going to call this J square, and the reason for that is not to be narcissistic. The reason for it is to not necessarily clash with built-in functions, because I believe SAS already has a function called square, it already has a function called pow, and we're going to do the same. We're going to make a square function and a power function to start with, and we want to prove that our functions are doing the work and that it is not, we're not just sort of faking it and piggybacking off the built-in functions. So that's why I initial these functions, just to be sure that that doesn't happen. And to write a square function, we've already said it's fairly straightforward. It's the number times itself. As always, each line is ended with a semicolon. We specify to SAS that we are dealing with a function, and we end that function with the end sub statement after we're done. Now this is a very, very simple function. You could have been doing a few things in here. You could have even said, well, y is, x power x, and you could have returned y, but that's a bit redundant. So we're going to stick with the very straightforward x times x. Now, if you wanted to make this a little bit more permanent, because remember, anything you store in work is going to be temporary. If you're in the advanced SAS playlist on my channel, this is something that you probably know already, but just a reminder. And you could always store it in something like SAS user if you don't have a particular path, but then it just won't be accessible to anyone else if you're trying to share functions with a team. So you may want to put this into a code repository, a shared drive location, something like that, where other people can get to it as well. Now we can run this. Sorry, there is no works library, it's a work library. We can run this, and you'll notice that SAS does create this .funcs dataset, and in this dataset it specifies some metadata like the header, the prototype name, which is our package name, and then it says, like, well, there's a function, there's some statements that are in there, source statements, function return end sub. I think it might even put in all of the code in here if I'm not wrong. There we go. So it's got, it starts function, return, and then it ends, and there you can actually see the code as well that's in this package. That's not the most important thing though. What we're aiming for here is, if we go and check our log, it'll say, well, the function J square has now been saved to this library dataset and package name over here. And we'll keep trying to extend this package as well as we as we go along. Excuse me. The other thing that we need to do is we need to now be able to point SAS to this new what do you call it? This function and packages collection that we've created, and we do that with an option statement. So you might have something sitting on a permanent library, a disk, whatever, somewhere, and you're not necessarily starting out by writing these functions out every time. You imagine this doesn't exist. You just want to start your program, and you are now using these custom functions. You need to point SAS, very similar to what we did with formats actually. If you go and watch my video on SAS formats, we also had to point SAS to where it should go looking for custom formats. And we did that with an options FMT-lib, options format lib, and we pointed it to where it could go and find those formats. So we do something similar here, and we're telling SAS, well, where you should go looking for compiled functions. What is the compiled functions library that you should go and look at? And in our case, it's work.funcs. I keep writing works because this is funcs. So now SAS will go and look for functions that we've saved in this library and dataset, this 2-level name. Now we want to test that the square function of ours works. Let's make a very simple dataset. We're going to call it numbers. And we're just going to run a quick do loop. Again, I've done a video on do loops, so if any of this doesn't make sense, you really should be at the SAS from Scratch channel playlist, rather, that's on my channel before you get to this section. So I'm going to run this again. We're going to see a warning, and I'll explain the warning, but simply it's because this function already exists. We're overwriting it if we run the entire program again, and SAS is just going to warn us about that. Should anyway. So this is our numbers, 1 to 10. That's fine, we expect that. I thought it would warn us about this, but whatever. Maybe later. Now, to call this function on our numbers dataset, we again need to invoke PROC FCMP. We are not defining a new function, we're calling a function. So instead of saying outlib and putting all of this stuff in, we run it similar to how we would run a proc sort, for example. We say, okay, well, what's our input data set? It's this numbers data set. And our output data set, we're just going to say it's the test of our functions. This should just be a quit or a run. This should be a quit probably, huh? Because proc FCMP needs to be quit. And then we can say, well, let's do underscore square is j square of n. So our function parameter in the local scope here, it's referred to as x, but we can pass whatever parameter we want. So we could have n, we could have y, we could even have something called x, but this numbers data set wants to pass this variable called n into the square function, and when it gets into the scope of our custom function, it will just be referred to as x and the value will be returned. So if we run this, you'll notice that we do now have underscore square, and it does return the square of whatever value we have in n. So if we have 1 squared is 1, 10 squared is 100, 5 squared is 25. Doing a quick desk check, it looks like our function works perfectly fine. Now, just to demonstrate that we can do multiple functions in a package, we're also going to write a function to do custom powers, so x to the power y instead of just square, which is x to the power 2. We're going to call this function jpower again, just to not clash with the built-in function, which is pow for power. We have nothing to do with the federal chair of the US Reserve, Jay Powell. However, if he is watching, I could use some investment tips. In this case, we are taking in two different parameters. So we need our base and we need the power, our exponent, because it's going to be x to the power of y, and we're going to return x to the power of y. This is the built-in operator for doing base to exponent calculations. So all of these functions are slightly redundant because they already exist within SAS, but it gives you a good idea of how the process works. In fact, what we could even do here is say, let's say z is x to the power y, and then we're simply going to return z. So let's run this. Now we do actually get our warning that says, okay, you've already defined j square in a previous package, and function j square as defined in this program is now the default. So we've got this saved, and we've got our new function jpower saved as well. We can now use it, so let's go and call this one pow, and we say let's do n to the power of n. So for 2, it's going to be 2 to the power 2, 3 is going to be 3 to the power of 3, etc., etc. And we can quickly desk check this. So 2 to the power 2 is 4. 3 to the power of 3 is 27, because 3 times 3 is 9, times 3 again is 27. And same goes for 4. So 4 times 4 is 16, times 4 again is 64, and times 4 again is 256. So that we think makes sense, and 10 to the power 10 as well should just give you 10 zeros at the end here, which I believe it does. I'm not going to count every single one of them. We have reasonable confidence that our function is correct. Now, this is all fine and dandy. The basics of functions work. Now we do something which I have a soft spot for, which is recursive functions. So you could do something that, for example, calculates the factorial of a number. And you could do a factorial calculation without using a recursive function, but honestly, it's more efficient without using a recursive function as well, but it's more fun to do it with a recursive function. So that's why we're going to do that my way. Also because this is my channel and I do not run a democracy. So the way a factorial works, if you're not familiar with it, the syntax looks like, you know, I guess you could call it the syntax looks something like this. It's a number followed by an exclamation mark. And what that basically means is that it is 5 times 4 times 3 times 2 times 1. And for any number that you pick, it's basically that same number times 1 less of that number, sort of repeated until you get to the number 1, and then you stop. So for 5, the value is 120. 5 times 4 is 20, times 3 is 60, times 2 is 120. For 3, it's just 3 times 2, which is 6. And likewise, if we want another example, we can pop in the factorial of 4 as well. 4 times 3 times 2 times 1. And you can actually just build on these, because 3 times 2 times 1 we already know is 6, and 4 times that is 24. And likewise, this this whole thing that you've got here is just 4 factorial, which is known as 24, times by 5 is 120 again. So they sort of build off of one another, and that's the whole point of the recursive function as well, is to say, well, let's go back and look at the previous answers for the factorial calculation. Now, the function we're going to again just initial, just to make sure. I don't know if SAS has a built-in factorial function, to be very honest with you. Just in case they do, we're going to write our own. So we're going to start off by putting in our termination case, which is, if you don't, a recursive function will just keep recursing until you cause a stack overflow. We're going to put in this base case that says, okay, if n is smaller or equal to 1, we're just going to return 1. So factorial of 1 is 1, factorial of 0 is 1 as well. And there is actually a mathematical proof for why that is the case. But it was a very, very long time that I actually took a class in which we covered it. I might have been numerical analysis, I can't remember. But there is a proof. You can go and look it up and you can figure out why factorial of 0 is 1. And we're also not doing a lot of sanity checking here. So we're not going to check if people pass negative numbers. We're not going to check if people pass numbers with decimals, floats. We're going to assume the user gives us a bog standard integer, 1, 2, 3, 4, 5, etc. So we're going to say, okay, if we get past any n smaller or equal to 1, then we are going to return 1. And you'll notice we use our normal, something like an if statement, for example. We can keep doing that just as we, excuse me, just as we would, for example, in a data step. So none of this is, really special from what you've learned before. The only thing we're doing is we're wrapping it in this function and end sub statements, and we're putting that inside of a PROC FCMP. And now the recursive statement, or the recursive case, is to say, well, if we're not at the termination case, you need to do basically call yourself as the function again for n minus 1. So this function that we've defined here also calls itself again. And so what that does is, if we've got, for example, n is 3, we step into the function. This is false, so we enter this function. And we say, okay, well, return 3 times, and then call yourself again. But n is 3 minus 1 is 2, so calculate it for 2. It enters the function again. So this result of 3 is placed onto the stack. This one will then be calculated for factorial of 2. This again does not get triggered, so we go into the recursive case, and what gets returned is 2 times the factorial of 1. So now we have 3 on the stack, we have 2 on the stack, and we're entering the function one more time for factorial of 1. We enter the function, we have our termination case, and it simply returns 1, and it ends. It does not enter the function again. Now, what that then does is it looks at all the values that's on the stack. So it's like, I've got 3, I've got 2, I've got 1. Start popping all of those off the stack, put them together, because our instruction was every time this number times whatever comes out of the function again. So 3 times 2 times 1, and that will return 6 out of this function. I don't want to go into too much detail specifically about the recursive functions. There's loads of resources on it out there. This is just to show you that the kind of functions that SAS allows you to write are pretty much all encompassing. It's like you would in any other language, basically. So let's make a variable called fct for factorial, and we're just going to do a factorial of n as well. So that's every time we're just going back to this numbers data set of ours that's running from 1 to 10. And I'm going to run this whole thing, and we should get a warning again. It just says, look, you have already defined the square and the power packages before. That's perfectly fine. We know we have, and now we've also saved factorial to the functions library. If we go and look at the output func test, we see that we've got n in this column, square, power, and we've got factorial as well. So 1, 2, 6, 24, 127, 20. And you can go and desk check all of these as well. They are correct. That is about it in terms of what I wanted to show for functions. The next thing that I wanted to show was subroutines. And the way that subroutines work are that they kind of work like functions. They store a set of instructions, but in SAS, the subroutines take many arguments if you want them to. You specify some of those arguments as something called OUTARGS. So arguments for output to be placed into. And what do we mean by that? We mean by that something like the following. Now, if I specify a subroutine, and I'm going to close it here at the bottom. If I specify a subroutine and I call it body measurements, and this body measurements subroutine takes weight and height, I can, for example, output something to BMI. And the way I do that is just to tell SAS, listen, sorry, I want to put 6 in here as well, and there's a good reason for that. But so these 3 will be input, and I tell SAS that this BMI column is actually an output argument. And what I can do is then put in a calculation in this subroutine that says BMI is weight divided by height in meters squared. And what we can even do is we can refer back to our own function that we've just written. You know, we can use this. We can use even j square if we wanted to. Height divided by 100, because we're going to pass this height in meters. Sorry, in centimeters. So we're going to pass it as centimeters, but we need it for meters in here. I'll get into the multiple output arguments just now. Let's assume for now this is what we're going to do. We will be doing a little bit more. And I will, let's say, calling custom functions. Now let's say, let's fix this properly, and let's say set location to look for custom functions and subroutines. This is where we call custom functions, and then we're going to do another one which is going to be calling subroutines. And we're going to need an input data set, so let's just make our own once again. I am going to use DATALINES for this, which I don't usually do because I always forget the syntax for it. But we're going to basically specify subject ID, sex, weight, and height, and we're just going to put in some random data in here that we're going to use. So we're going to say, okay, well, I've got subject 101. That subject is a male of weight 80 kilos and height 180. I've got subject 102. Let's say she's female, and we'll say 65 and 165. 103 is again male, weighs 120 kilos, for example, 175 centimeters in height. So he is a big lad. And let's do 104, female, 45 kilos and 100 and, let's do 165 as well. So this is my data lines. I'm going to just run that so that we can take a look at this data set. So we've got subject, sex, weight, height. We got all of that. And this is what we're going to need for the subroutine as well, because recall when we specified this subroutine, we said we're going to pass weight, which is numeric, height, which is numeric, sex, which is character, hence the dollar, and BMI is numeric but is an out argument. We do have to, when we call this custom subroutine though, we do need to specify this BMI column somewhere. Now for this, we're not going to do it in PROC FCMP. We're going to do it within a data step. So I'm just going to call this body measures 2. It's going to set body measures, this data set we've just created, as its input. And then we're going to call, and this is an important keyword, we're going to call this subroutine. So notice how it's different to how the functions work, which have to be called via PROC FCMP, and you just call the name of the function. In this case, this is within a data step, and you call the name of the subroutine. We're going to pass, our columns are called weight, height, sex. We're not going to worry too much about subject ID now. We don't need to pass subject ID. It'll just be carried along in each row. But weight, height, sex, and let's call this BMI. Let's call it my BMI, and we'll see what happens. I probably need to just call PROC FCMP again because I need to replace this subroutine. So it calls it function body measurements, even though it's a subroutine. And let's just see what it looks like in here. So this name also, it says subroutine, and it's got the OUTARGS and stuff in there. Not to worry about that too much. Body measurements we've already got in our work library. We haven't cleared it, so that's still in there. And now if we run the data step here, which calls our custom body measurement subroutine, you'll notice that my BMI, which was an output argument, so we did specify a name for the column, but it's an output argument, received the BMI calculation result as output. Now, what makes subroutines so special is that you can add more stuff in here. So we can say, okay, well, I also want to calculate ideal body weight and lean body weight. Now, your ideal body weight, I believe, is what your body weight would correspond to given your height, and I think they count a healthy BMI as around 22, an ideal BMI. So not too thin, not too fat, to put it bluntly. And then they say, okay, well, at 22 BMI for your height, what would your weight be? That's your ideal body weight. Your lean body weight is obviously, I think, I would assume that's probably just between normal BMI and maybe underweight BMI, but I'm not 100% sure about this one. Now, I've got the calculations here on the side. You can't see them on the screen. I'm again not going to do a lot of sanity checking. What we're going to do is just say, okay, well, in addition to BMI being an out argument, we also want ideal body weight and lean body weight, IBW and LBW, to be output arguments. And what that allows you to do is to have multiple output arguments. Now, this function here returns a single value, but with a subroutine, you can have multiple outputs. And that's what we're going to do now. So we're going to say, okay, well, if sex is male, and this is why I kept the height in centimeters as well, because the ideal body weight and lean body weight calculations, the formulae that I have are they use centimeters, so it just made it easier for me to specify it in centimeters. You're probably just going to have to take my word for these calculations. I found them somewhere online. So let's just hope that they're correct. And again, just keep in mind here, if sex isn't M, because we're just doing a blanket else, if sex is Z or sex is alien, it's just going to take the female formula. So the only reason why we're doing this is because this is in a practice scenario and we know that our inputs are clean. So it's male or female, nothing weird in terms of the values. That's why we're just using a dead simple formula like this with absolutely no sanity checking. In a real situation, you would be a lot more strict on this. You would say if sex is male, if sex is female, else, you know, notify the program and the log, have them look at the input, because there's probably a problem there. I don't know if this formula is exactly correct because it looks very, very similar to what the male one is. I might have typed this incorrectly, but it doesn't really matter because what we are trying to demonstrate here is the multiple outputs that that the subroutine supports. And then we're going to do the same for like for the lean body weight. And there's a formula for that as well. And again, I did not double check these formula. I have them here on the side, copy them from the web somewhere. We'll have to hope and pray that they're correct, I suppose. But if they're wrong, it's excellent practice for you to just go and fix them on your own time and recreate these functions and subroutines as well. So let me just double check my work here. We've added these new parameters in here. We've specified that they are actually output parameters or output arguments. We're still calculating BMI, which is linked, of course, here. We've got a value for IBW, which is linked here. So it doesn't matter if our user calls it my BMI. Within the scope of this subroutine, it's going to assume that that is BMI, and that's the name that it's going to use as well. It's going to put that into this parameter, and then this reference to this column will be populated with the result. So we've got BMI, IBW, LBW. We just need to replace this function now. Well, the package and the subroutines. What did I do? Oh, sorry. We do have to say else IBW equals. The only warning is probably that the functions already exist. That is fine. In real life, you won't continuously be overwriting your functions like this. You'll hopefully have a library and then you will call that library. We're also going to now add my ideal body weight, and we just need to check the position of the parameters. So ideal body weight and then lean body weight, and my LBW. So let's run this again and call this again, and we should see all of these values. So there's BMI, lean body weight, and ideal body weight and lean body weight. So you'll notice here this person with weight 80 kilos, the ideal body weight is 75, so about 5 kilos, you know, depending on whether you subscribe to BMI or not. I know that's a contentious issue these days. This person could probably do a shaking off 5 kilos. If this person wanted to strive towards lean body weight, they'd have to shake off about, 18.58 kilograms, if I'm not mistaken. Don't know. It's been a long day. It's 8 p.m. my time, so. And it was a work day as well, in my defense. likewise here, so we've got a person here who's she's 65, lean body weight 56, ideal body weight 56, lean body weight 46. We've got here a rather heavy lad. He's at 120. He should be at 70 or 76. So this is something that now makes me wonder, because I'm trying to figure out why the ideal body weight here is less than the lean body weight. Good question. I'm not too concerned about the results at the moment. What is important is just that you notice that within a single call to the subroutine, we have basically calculated 3 different values, and that will make your life a lot easier, especially if you're in a position where calculating things like BMI, ideal body weight, lean body weight, if that's something that is a standard daily thing for you to do, instead of copying and pasting code, instead of having every single programmer do it their own way, possibly with mistakes, what you'd rather want to do is create a function package like this, which you can share with your programmers. Obviously, you would need to validate this. You would need to put it through testing, especially if you're using it in a production environment. But what that then allows you to do is you save a ton of time by storing these subroutines and functions and things that are particular to your skill set or work responsibilities. And that's then being used by you or your team or colleagues every single time when you need them. Instead of having to copy and paste these formulas every time, making sure the brackets are matching, etc., etc., you have a validated system that you call every time. The only thing that I want to highlight here is you'll notice that these variables are all uninitialized. So ideally what SAS wants you to do is to initialize the columns that these values are going to go into. And a good way of doing that is to call a built-in SAS routine, which is the missing SAS routine. So you can say call missing my BMI, and call missing my IBW. And now if you're looking at this, you say, well, then surely there's a better way of doing this than constantly typing these names and things. You might even be able to specify it with a bunch of commas. But since this is the advanced playlist, we can just as well do it with an array. So we can say, well, these are the variables we want to initialize. They are my BMI, my ideal body weight, and my lean body weight. And so what we then do is we're going to loop over these, and we can just say, well, do over all these variables and call missing init vars. And that's going to say, okay, well, call missing my BMI, call missing my IBW, call missing my LBW. And that'll basically create empty columns for each of these 3. And when we pass that to the subroutine, SAS is not going to complain about columns being uninitialized anymore, because SAS ideally wants those columns to exist when you call this subroutine. So that's about it for what I had planned today to look at. It's actually been fun doing some of these SAS videos again. And especially something like this that's not talked about too often, that's not, at least to my knowledge, not too widely published on things like YouTube. Obviously, if you Google, you'll find it. Even, to be honest, even in the SAS Advanced Guide, it's sort of, it's literally almost hidden at the back of the book. And you need to know it for the SAS Advanced exam, and it's a question that comes up in the SAS Advanced exam. But they have this very, very simple example, which is, let's take a first name, let's take a last name, join them together and return a single full name variable. And that's what's in the SAS Advanced book, at least in the version that I have. And it's not that old. It's maybe one version behind, maybe. It could even be the latest one. And so that's basically all they do in terms of functions and subroutines. And yet it is so extremely useful, again, if you're in the real world, where you don't want your programmers and your team to sit and copy and paste these formulas every time. Or, some people will put it in a macro. Some people will call a macro a function. Irritates me to no end, because a macro is not a function. A macro is a text preprocessor. It's a glorified copy and paste. This is a function. And we need to be very clear on that as well. So if somebody says macro function, you need to, raise an eyebrow and just make sure what they're talking about. Because if you do something like, I don't know, I need to think of a function. If you do something like compress, sure, that's a macro function, because it is a function that operates within a macro. It calls that that other function. But something like macro, my macro, my square x men, this is not a function. It just isn't. I'm sorry. So the whole point is to know the difference between what an actual function is, and a lot of SAS programmers, instead of writing a function, will write a macro. And honestly, you need to figure out which solution is most appropriate. Now, macros are often the most appropriate solution for SAS programmers. That sort of text pre-processing, that sort of, copy paste without you actually manually copying and pasting, is often extremely useful. But that does not mean that these functions are not very useful as well. And the nice thing about it is you don't need to keep referring to, a macro file, or including a macro file that sits somewhere. You can have your programmers point to a single library where all of these functions, all of these packages basically sit. And that's just so much easier, in my opinion, than the alternative. That's it for me. If you've enjoyed this video, please like the video. You can subscribe if you want to see more when they come out. Lately, I've just been getting nostalgic about some of the old DOS games I used to play. So there's a bunch of DOS games on my channel, but I will probably get into some of the other advanced topics, arrays, PROC SQL, macros, obviously. So there's a couple of things that you kind of need to know for SAS Advanced. And I'm probably not going to go into as much detail as I did for the SAS-based stuff, but it might be good to have a video that says, hey, here's how arrays work, here's the basics of macros, here's the basics of PROC SQL. So fewer videos, hopefully not too long in length. But I do want to get to it at some point. Anyway, that's all from me. So as always, thank you very much for watching, for bearing with my waffling and rambling and my rant at the end about macros and people wrongly referring to macros as functions. Until next time, I hope you have a very good day wherever you are. Thanks. Cheers. Bye-bye.